Hello, my name is Tom Dagès, and this is a short talk on metric convolutions, a unifying theory to adaptive image convolutions, our ICCV paper with Michael Lindenbaum and Alfred Bruckstein. So the goal of this work is to revisit our understanding of what is a convolution, and more specifically, image convolutions. From a traditional perspective, a convolution is a circulant operator, and it is often understood in image processing as sliding a kernel over the image grid. If you recall your first undergrad courses, convolution was probably formally introduced with this formula, whether it be in the discrete or continuous world, which from our perspective in this work are basically the same. However, in the modern deep learning era, we changed the convention to call convolution what was usually named as correlation in order to more easily fit the mental image of the above animation without having to flip kernels. In practice, the standard image convolution operator uses a k-by-k grid as a kernel, typically 3x3 in neural networks, to perform local averaging, which is what we will be focusing on. And from an operator perspective, a convolution is a linear shift equivariant operator, thanks to its sliding kernel window with shared kernel weights, meaning that wherever we place the kernel on the image, the weights of the kernel are the same. Importantly, convolutions do not depend on the incoming signal, meaning that if you feed two different images to the same convolution operation, then the exact same averaging kernel will be applied to them. Unfortunately, there are a few downsides with the standard convolutions we are so used to. Let us look at a simple example on the bottom left. We have this image of a duck, and maybe our convolution belongs to some pipeline that needs to do some kind of segmentation. In this case, when extracting features using a convolution, sampling from the background outside the duck segment will introduce undesired noise. Unfortunately, because of the rigid structure of the kernel in standard convolutions, this becomes unavoidable next to segment boundaries. Another issue with the rigidity of standard convolution is that it does not account for scale. For the point at the center of the duck, the size of the kernel might be too small, focusing on some local detail of the duck texture rather than looking at what the duck is as a whole, which is more desirable in, say, a segmentation task. So, to overcome these limitations, the community has proposed ways to tweak the kernel at different locations in order to better fit the particularity of the pixel location in the specific image. This is achieved by allowing the window of the sliding kernel to change adaptively. However, doing so will make the adaptive convolution signal dependent, which implies that these non-standard convolution operations are no longer linear. However, they still share the other properties of convolutions and can thus still be understood as a form of convolution, since the only thing that is changing are the sampling locations, not the kernel weights. Now, let's have a look at some of the tricks from the deep learning community to tackle the three problematic examples on the duck image. So, in order to sample a larger region and avoid focusing on small-scale details, we can dilate the kernel by some scaling factor. This leads to the famous dilated convolutions and has become common in practice. However, almost all works and libraries only use a global scaling factor. Some much rarer works propose ways to make the dilation factor depend on the pixel location based on the data that the convolution is seeing. The scalar factor is thus adaptive and no longer uniform. For this second problem, to avoid mixing samples of the semantic object and of the noisy background, we can shift the convolution kernel adaptively by offsetting by some vector, leading to what we call shifted convolution. However, in complex regions like on the beak of this duck, we will not be able to find a good location that does not sample the background by only shifting the kernel. Instead, we want to deform the k-by-k grid by offsetting each cell of the convolution grid to better fit the local structure of the image data. This leads to the operation called deformable convolution. As such, various ideas were proposed to overcome the rigid limitations of standard convolutions by changing the sampling locations of the sliding kernel window. However, this diverse field can seem sometimes like a multitude of performance-driven tricks, but as a scientist and a mathematician, what is crucially lacking in the community is a unified theoretical framework. Providing one that is also geometrically interpretable is the main goal of our work. We will thus revisit these methods in a systematic way from a metric perspective. So, whether continuous or discrete, all these traditional convolution techniques are effectively sampling some implicit local neighborhood of the pixel of interest. The thing is, a neighborhood is a set of locations close by, and closeness is a concept that is defined from a distance measure, which is also called a metric in mathematical terms. So, different and changing sampling neighborhoods imply different and changing implicit metrics. From this metric perspective, the different traditional convolution techniques are sampling the regions contained within a level set of this metric. And without loss of generality, we can fix this level set to be 1, meaning that these traditional convolutions are essentially sampling the unit ball of implicit metrics. In standard convolution, unit balls can be seen as disks that will always be the same over the entire image. The metric is isotropic and uniform. In adaptive dilated convolution, the unit balls are still centered disks, but with different sizes at different locations. This means that the implicit metric is an isotropic yet non-uniform metric, just like, for example, the famous Perron-Malik anisotropic method, although the naming is unfortunately misleading as they are in fact isotropic. In shifted convolutions, the associated unit balls are offset and can be approximated by some off-centered ellipses. And in deformable convolution, the associated unit balls can be heavily deformed to fit the complex sampling region, leading to high anisotropy levels in the metric and offsetting in the unit balls. All the presented examples where neighborhoods are convex can be understood from an implicit metric's perspective as unit balls in the tangent space of the metric. However, in some extreme cases, the sampling region in practice of some deformable convolution might not be perfectly explained as sampling the unit ball of some convex neighborhood. From a metric perspective, this means that the sampled unit balls are allowed to be non-convex, which in turn means that in these cases we are looking at the unit geodesic balls rather than the unit tangent balls. In any case, we have found that the traditional convolutions can all be understood from the same unifying geometric perspective as sampling unit balls of some implicit metrics. The thing is, with this new understanding of what is a convolution, we propose to shift the paradigm. Instead of relying implicitly on some metrics, why not design a new convolution operation that explicitly depends on some metric, providing, among other things, geometric control and interpretability? This leads to our metric convolutions, where the operators will first compute explicitly some metric, then its unit balls, tangent or geodesic, although from now on we will only focus on tangent balls for simplicity, and then sample the unit balls to compute the convolutions. However, before we can dive into more details on metric convolutions, we need to clarify the types of metrics we use. You're probably familiar with distances being symmetric by definition, which implies that unit tangent balls are also symmetric. However, to explain shifted and deformable convolutions, we required offset unit balls. This means that the distances we need to work with are in fact asymmetric. As such, we must go beyond the usual metrics like the common Riemannian metrics and must instead use asymmetric Finsler metrics, which are much less well known in the computer vision community. As such, before we continue, let us briefly present this asymmetric generalization of traditional differential geometry that is Finsler geometry. So let's keep it simple. Fundamentally, differential metric geometry lies on the study of lengths of shortest paths on curved manifolds, or, for example, surfaces. To measure distances, we need to know what is the distance of vectors in the tangent plane. Usually, all directions are the same, meaning that tangent vectors in a circle all have the same length. The metric is isotropic. However, it is sometimes preferable to favor some directions. The unit ball in the tangent space is no longer a circle and the metric becomes anisotropic. Yet a vector and its opposite share the same distance, preserving the symmetry of the metric. Such metrics are commonly used in the field as Riemannian metrics, which have a simple closed expression given by a quadratic form. If we go a step further, we can obtain Finsler metrics, where a tangent vector and its opposite no longer share the same length. Unit balls in the tangent space are now off-centered and asymmetric. The consequence is that traversing a curve in one direction or the other no longer leads to the same length, implying that shortest paths from A to B and from B to A may not be the same. Although Finsler metrics are uncommon in geometric computer vision, many systems are asymmetric in practice. In our work, we considered the simplest parametric Finsler metric, the Ronda's metric, that generalizes the Riemannian one. To the Riemannian metric, it adds a linear term governed by a drift component omega. Nevertheless, our work applies to any general Finsler metric. To create one, it suffices to focus on the tangent space. There, unit tangent balls must be convex due to the triangle inequality axiom. The homogeneity of the metric, leading to symmetric centered unit tangent balls, is replaced with positive homogeneity instead, breaking the symmetry and allowing the unit tangent balls to be offset. From these axioms, any convex set containing the point of interest is a valid unit tangent ball, and by the positive homogeneity, it entirely defines a Finsler metric on the entire tangent space. In other words, unit tangent balls are all you need. Note that by integrating the length of tangent vectors along the manifold, defining such convex sets also defines the geodesic Finsler distance along the manifold. In practice, you can use any parametric family of convex shapes for our metric convolution operators, although in the paper we only focused on the simplistic Ronda's metrics, yielding elliptical unit tangent balls and generalizing Riemannian metrics. So that's it for the presentation of Finsler metrics, and let's go back to our metric convolutions. So how does it all work in practice? Traditional convolutions are usually implemented using this core pipeline. Given the reference k by k grid, we find offsets for each of its cells. This can be done either in a signal independent fashion with some heuristic design, such as say global dilation, or in a signal dependent fashion by computing offsets from the data using a standard convolution which preserves shift equivariance. We can generalize this schematic pipeline to our metric convolutions. Given an image, we can use either geometric heuristics such as image gradients, directions, and magnitude, or an intermediate standard convolution to compute the parameters of the Finsler metric. Using these parameters, we can directly and explicitly compute the unit tangent balls, and we can then sample them at analytical positions. Our construction is both geometrically interpretable with complete control on the metric and compatible with usual learning approaches. So let's look at the learnable framework with slightly more details. This is the implementation pipeline of a deformable convolution. In order to compute the offset vectors of the k by k grid at each pixel, the intermediate standard convolution needs to compute two k-squared numbers per pixel location in the image, corresponding to the k-squared offsets, meaning that it has to compute two k-squared output channels. This becomes prohibitively expensive for high k, explaining why in practice deformable convolution is mostly used with the smallest k equal to 3. Afterwards, sampling is done using interpolation, and the output is obtained by kernel-weighted averaging of the input samples. Imitating the design of deformable convolution, our metric convolution computes the parameters of the Finsler metric. For Ronda's metrics, we only need to compute 5 numbers per pixel, and thus a 5 output channel standard convolution is used. 3 numbers for the entries of the 2x2 symmetric positive definite matrix M, and 2 numbers for the Ronda's drift component vector omega. Regardless of how many samples we are going to use for the convolution, we do not need to increase the number of output convolution channels, making our operator graciously scale with sampling size. Afterwards, the explicit metric parameters provide analytical unit balls, and sampling then can be done analytically using any preferred scheme. Most importantly, our pipeline is fully differentiable, and so we can replace existing convolution operators in a plug-and-play fashion with our metric convolutions, for instance in any neural network. So very quickly, in practice, we experimented metric convolutions for image denoising and classification. Here we show the unit balls of Finsler metrics obtained with a simple non-learned heuristics based on the image gradient. As you can see, we can sample a neighborhood that does not mix between the object and its background. Here, in the bottom colorful images, are GradCam visualizations of trained ResNet models with various types of convolutions on data from 3 random classes on the CIFAR 100 dataset. Our metric convolutions better focus on the objects related to the class label rather than the background. Additionally, our metric convolutions are able to locate several instances of the same class as demonstrated in the bottom right image, unlike its traditional counterparts. If I were to summarize, what our experiments in the paper show is that our metric convolutions provide many advantages over traditional techniques without degrading performance. These include geometric interpretability, control, inductive biases, training regularizations, and more. In conclusion, we revisited traditional techniques to design convolutions with adaptive sampling locations. By taking a geometric approach, we understand that this zoo of techniques fall under the same unifying principle, which is that they all sample unit balls of implicit metrics. Focusing on convex unit balls is simpler as it only requires studying tangent spaces. Non-convex unit balls are also acceptable, but require investigating geodesics, which are obtained by integrating what happens on tangent spaces. As techniques often do not preserve symmetric sampling around the pixel of interest, we need to allow for unit balls, including tangent balls, to be asymmetric. To obtain asymmetry in metric geometry, we need to depart from classical Riemannian geometry and generalize it to embrace Finsler geometry, a largely uncharted yet naturally occurring field in computer vision. Thanks to our new perspective from metric geometry, we designed a new type of adaptive convolution that relies on explicit rather than implicit metrics. Doing so not only boosts the geometric interpretability and control, it is also beneficial to learn convolution layers thanks to its geometric inductive bias. Our metric convolution operation can either be designed with simple geometric heuristics or can be learned within a deep learning framework. Please visit our project website where you will find the paper and the code for more details on our work.